Thank you. So this is going to be a little more of a background predictions talk. I just last week started dipping my toe into playing with the RAD-seq data that I have. So bear with me as I sort of give a little more background, and then I'll get into a little bit of the stuff that I've started to do exploratorily. And I'll be very excited to hear any suggestions or ideas that you all might have. So I have to have the obligatory beautiful Manakin slide, even though we all know that they're wonderful and that's why we're here. So the species that I'm going to be talking to you is the White-ruffed Manakin Corapipo altera. I work on them in Costa Rica. And so, like many manakins, eat a lot of fruit. These guys are in wet, montane tropical forests that are quite rainy. And they do displays on fallen logs. And they can do either solo displays or multi-male. So I have a little video that hopefully will work of just a brief clip of them displaying, because who doesn't want to see cute mannequins? So this is a multi-male display on a log, female visits. They're doing really cute little butterfly flights. It's wonderful. Okay, so a little more about White-ruffed Manakins. So this is sort of their life history trajectory, just so everyone is on the same page. So they hatch and then they have second-year plumage, where they're just starting to get a little bit of a mustache. By their third year, they have a pretty awesome Zorro mask. And then in fourth year, they start actually looking like grown-up male mannequins. This is just males. Females, of course, are all green. But it takes quite a while for them to reach, become an alpha at a log and actually have success with any potential female visitors. So just keeping that in mind, that it's a pretty long life history stage to get to a point where they can actually reproduce. So a little background information about these guys. Previous studies of Alice's and Megan Jones, who is a student in Ball's lab, studied a population in Costa Rica that experiences a remarkable amount of rain, over 8 meters of rain every year. And so in this population, they found that during preceding and during heavy rainstorms, we see evidence that this is quite stressful physiologically for these birds. And as a result, some individuals, not all, but some individuals, and often males, will migrate downhill where it's less rainy to escape these physiological stressors. But this facultative migration has a consequence in that when those males come back for the next breeding season, a lot of times they're losing social status. So they're paying a cost to avoid heavy rainstorms. So I came in and we started thinking about what that rainfall might mean in terms of demography of populations and in terms of sexual selection, which I'll get to in a moment. But first we looked at estimates of apparent annual survival for different populations. And so in this super rainy population, where they're getting tons of rain, apparent annual survival has been calculated at only 62%. And if we look at a different population that in a different area of the country that gets about half as much rain, they have significantly higher 94% estimates of apparent survival. So what might these differences in demography mean for sexual selection and reproductive skew? So if we think about two little populations of cute little white-ruffed manakins, we have our rainy population up here, our less rainy population down here. We could predict that perhaps in a population that is not experiencing this dramatic cost of rainfall and has much higher survival, we would see increased sexual selection because there's a little less natural selection, and our reproductive skew might be a bit higher. So we have a rock star male, there's lots of reproductive skew in the system, he's surviving for 10 plus years, and we might predict that he would remain a dominant alpha male at a log for many years and increase the reproductive skew in the system. Whereas in our rainy population, where there's going to be a lot more turnover in who's an alpha year to year because they're migrating downhill and they're coming back and they're betas sometimes, we might predict that within a single year there'll still be reproductive skew and there will be certain males who are more popular, but across multiple years there may be more males that are all getting a chance at being that superstar. So then we would predict that there might be a little less reproductive skew overall in that population across multiple years. So how can we test this? Doing paternity analyses would be awesome, but their nests are quite see-through and they tend to be 8 to 10 meters up in the canopy. So that's not super feasible, unfortunately. And so instead, we have gone in this more genomic, genetic direction. This is a concept that I came across first in this Huang and Robowski paper in 2015, and it's something that's been discussed throughout the Manakin RCN for many years. And in both of those cases, they're talking about a cross-species test of this. And so I'm going to be giving you a look into how I'm thinking about testing this within species. So just keep in mind, you can expand this up to the next taxonomic level. But anyway, so we want to use the genetic diversity of the sex chromosomes relative to autosomes to measure reproductive skew. So we've got our ZW system, and if instead of cute little male mannequins, we think of them instead as sets of Z chromosomes, we can go back to this prediction and think about how in a not less rainy population where we have our higher reproductive skew, we would have fewer Z chromosomes being produced in that population and propagated across years. Whereas in our rainy population, over multiple years, you're going to end up having a higher effective population size of Z chromosomes. So this is where we're getting this prediction and where we want to go with testing the genetic diversity of Z chromosomes and relative to autosomes. I haven't quite gotten there yet, but I'm going to walk you through what I've gotten so far. So to test this prediction, I've gone and found 7 different locations in Costa Rica throughout Costa Rica, and I've managed to find places that are along replicated rainfall gradients. And so we have this gradient of drier up in the north down to a little bit wetter in the southern part of the country. And this dashed line is representing the Caribbean and the Pacific side. So these Corapipo, altera, and Costa Rica in some cases have been considered different subspecies on either side of the central mountain range. There's not currently a lot of gene flow going back and forth. So that's just to show you that. So we went and caught some birds and took some blood, and this is a good point to mention this Corapipo altera genome, which we were able to develop, which is really excellent. And so this is just a lot of statistics that Morgan has already covered in much better detail than I will currently. But we were able to use that genome as we prepared to sequence all of these samples. We used it for an in silico digest to figure out what enzymes we wanted to use to get the ideal number of markers and depth of coverage and stuff. So that was a really excellent thing. We were able to loop that right into our research project at the perfect moment. And so then this is some of the stats for those analyses. So I had a total of 158 samples from these 7 different populations. So the range was 15 to 35 individuals per population, all of that stuff. I'm running out of time, but this is the pipeline. And we ended up having 247,000 markers, 65,000 loci, good amount of data. Okay, so now I have recently learned how to play with the BCF file, and thus far, I've managed to do a principal components analysis of biallelic SNP diversity. And so each byte is an individual, and we're just looking at across the entire genome. This has nothing to do with the Z or the autosome diversity yet. This is just across the genome, looking at diversity. And already a pretty interesting pattern is popping up in that these are all of my Pacific slope populations, and they are all very similar. While over on the Atlantic Caribbean slope, we've got way more differentiation between our VT, RA, and EC populations. And this is a little bit different than what we would even predict, because where we see that altitudinal migration that I discussed earlier is in this RA population. So we might predict that if it's a population that's already moving, somewhat annually, maybe we might expect more gene flow and dispersal throughout that Caribbean population. Whereas in the Pacific slope, it's much less explored and known that they do any of this altitudinal migration. So that's an interesting pattern right off the bat. And then this is another thing. So this is a discriminant analysis of the principal component. So it's just sort of telling us a priori which populations the samples came from, so we can look at the probability that they're assigned to the correct population. So again, you see this really clear differentiation of the 3 Caribbean slope populations. The CG population, which is the farthest north Pacific slope, it's fairly differentiated, but then these farther south ones, there's way more mixing. So this is all very interesting, and I have a lot to explore, including figuring out which scaffolds are related to the Z chromosome, which Kevin is helping me out with that already, which is really great. And yeah, then actually being able to test this question that we've set out to and do that. And look at how population genetic diversity might be related directly to these rainfall differences across the country. So with that, I will be happy to take any questions, suggestions, feedback. Thank you all for listening.